Alright, so in this video I'm going to be explaining this important paper with the title Simplified Diffusion Schrodinger Bridge. This paper in 2024. So this paper introduces a novel theoretical simplification that facilitates its unification with the score-based generative models, addressing limitations of diffusion Schrodinger bridge in complex state. By employing this score-based generative models as an initial solution of diffusion Schrodinger bridge, our approach capitalizes on the strengths of both frameworks. So we also propose a parametrization technique that, despite theoretical approximations, practically improves the network's fitting capabilities. So why do we love diffusion Schrodinger bridges? Sometimes you don't need to start from a noise and denoise it until you get to the P data. Sometimes you have another data distribution, for example, blurry version of P data, let's say P of blurry of data. So we start from this. So this is our P0 and this is our P1. We want to reach it. We don't need to start from that. And the other important thing, there is unpaired problem in many problems, because paired problem is very easy. So unpaired problems, you don't know which one goes to which one. And so why do we love Schrodinger bridge? If you use optimal transport, using optimal transport to solve it, it's a static map. For example, this maps to this. If you start from this distribution, then it ends this. Start and end of something, if in molecular dynamics, is not enough, because in molecular dynamics or protein dynamics, the trajectory inside that should also be valuable, because you cannot because in molecule dynamics, in the mid time, at any time you say, it should also be a valid protein. So that's why in the middle is also important. So there are two motivations for this Schrodinger bridge. One, we don't want to start from noise. We want to start from something that we know, like a blurry version of your data set. And the other important reason is that the intermediate trajectory, the intermediate values is important. So once you want, by the way, this Q is a reference because you want it to be like a Markov process. You want to be as similar as possible to a very known Markov process, like a Brownian bridge. And so here is a dynamic formulation. We call it Schrodinger bridge. So we want to be as close as possible to this distribution Q, which we call it reference. In many papers, they call it reference. And the things that we know about that, we know the initial distribution should satisfy, for example, blurry images, data distribution. P1 should satisfy the real data distribution. Also, this line, look at this line, it looks like a stochastic interpolant. But, sometimes for discrete space, in discrete space, it's not easy to write it explicitly like this. And so this is from this slide of Guan Horing Liu, he's doing PhD in aerospace engineering, but he has written a very interesting paper on Schrodinger bridge that he uses solution of the that I will explain. So in our reference here, P, in this notation, the reference is P, so it can be a very simple forward. F can be just any linear drift, and your diffusion term is sigma t. And so this is a diffusion process, just forward step. but your Q should be as close as this to P. The KL divergence shows that. So we only need to know this term. If we know this term, then we know the initial distribution is good, the final distribution is good, and the intermediate is acceptable. It's a Markov process. Looks like a Markov process. So the optimal path measure, if you write it like this, psi is a potential, and we are very lucky that we know the solution of that as a PDE. So the solution, if we like as a potential, then we have this solution. The solution satisfies this PDE. And those two distributions, pi 0 and pi 1, that we map one sample to another one in optimal transport, here we call them rho A and rho B. So this boundary condition of this PDE is involved. It means that it will, so we will learn it by loss. Later we will parameterize and learn it, that once we solve psi, this PDE, then we have psi for the reverse diffusion as well as for the forward. By the way, the forward is also learnable in Schrodinger bridge, in contrast to the conventional thing that people don't usually learn the forward process in diffusion. But here we learn it. That's why Schrodinger bridge is much more general than both diffusion and flow matching. So how to solve this PDE? You know, again, it's a very old idea. Feynman, Koch, it goes to some physicists, that they solve that in order to solve this PDE is just a solution of this STE in this term. So the solution, V is the solution, V is this solution. So it conditions on X, but we get the expectation of Y. And so this leads to this forward-backward STE. They call it forward-backward STE. And then you write the path integral formulation. Then you parameterize it and learn it. It's I will explain it in the when we reach the video that I should explain, the paper that I should explain. This maybe paper number 87, part 87. I will explain. So background on Schrodinger bridge, I also said that B0 is a drift. So it's just we need a reference process. Any simple thing that we can say this is our reference process that has law P0. And the Schrodinger bridge process seeks a process xt such that x0 could be sampled from mu0, x1 could be sampled from mu1. So we need this process xt. So this is the correction drift that we need to add, as I said. So the total drift now looks like this. I mean, in their notation they had psi, now they have phi. So you understand. So its interpretation, we can say that B0 derives the process according to reference, and we have this correction term to steer the process. It's like a nonlinear control system. If you look at it in that framework, then it's just a minimization of expectation of the energy of your the batteries of your robot, for example, or the energy in a physical system. So U is here, the control input. And if we know the optimal solution is just the gradient of log phi. So the problem of Schrodinger bridge, as I said several times, you just need to find a distribution P such that at initial matches mu0, it's a marginal. At the terminal, which matches mu1, but at the middle, it want to look like your reference. We want to look like a Markov process. So yeah, you have this Schrodinger bridge, and the process looks like this. This is another formulations, different terminology, and then So it's so you see it's a dynamic version of optimal transport that just matches this one to this one and doesn't care about the intermediate thing, which is very important for molecular dynamics, because it should be valid in between. We are also or even in the if you want to know the trajectory of single cell data, if you like computational biology, that is another application that you want to know the intermediate, especially in healthcare that has strict rules. So this forward and backward and coupled through boundary, if the reference process is a diffusion, then it can be solved by the forward-backward PD. As I said, that Fokker-Planck equation. And it's also related to stochastic control, as I said. So we need a probability measure that at the prior it is equal to pi 0. I mean, let's see, this is the blurry images data set, and this is the images data set. So mu1, mu0. Another constraint that it need to satisfy, so this is the intersection of all constraints. It should be Markov. That's why we did that KL divergence of P and a reference Q. This is a reference that can be reciprocal. For example, Brownian reciprocal, that it it is pinned at the initial and the terminal. It is pinned, and it can be a Brownian motion, any Markov process. So there are two approaches to solve that. For there are iterative Markovian, but iterative proportional fitting. But this one is more general, because this one is inside this category. It's a particular case when it is discrete. So let's continue. Let's start our paper that I said. The paper, this paper that I introduced. They want to use score-based generative models that it connects to distribution through a dual process: a forward process that transitions the data distribution toward a prior, and a reverse process, typically guided by a neural network, that converts the prior back to the data distribution. These two processes can be modeled as Markov chains. So we know all of these reverse time distributions. So the diffusion and denoising can be formulated as a continuous time Markov chain. So we have this SDE, and the backward process is conceptualized by solving the time reversed, and this is our score matching. So in Schrodinger, as I said, you want to find arc mean of KL, I mean which pi is that, so we get pi star, such that the initial satisfies, for example, data distribution of images, and prior is our blurry. We know it's blurry images. But we don't know which one maps to which one. So generally, Schrodinger bridge problem lacks a closed form solution. Researchers employ the iterative proportional fitting to address it through iterative optimization. So we do this iterative optimization, but the IPF method needs to compute to optimize the joint density, which is usually infeasible. So diffusion Schrodinger bridge can be conceptualized as an approximate implementation of IPF. So when we have a pi is disentangled into these two, in the forward and backward trajectory, we can verify that when the conditional densities is optimized, the joint distribution can also be optimized. So we have backward and forward. So P and Q are the forward and the backward. This is the forward, and Q is the backward densities. So in practice, DSP uses two neural networks to approximate it, and And so this is a proposition. Oh, this one is this interconnected PDEs that I mentioned. So previous works have pointed out the optimal solution of Schrodinger bridge of this STE. We can see that here x0 is p data, xt is our prior. Now look, don't forget this boundary condition, otherwise it doesn't make sense how pi 0 and pi 1 we want to relate pi 0 and pi 1. So at the boundary you have pi 0 and pi 1. P data is pi 1. So we have at the boundary, if time is t, then we have pi 1, pi 0. If we have time is 0, pi 1. And so you know the boundary. You just need to solve this PDE. And I said there are hundreds of methods for solving this PDE. So we can achieve this P at time t. So we start analyzing training function of that. We introduce a streamlined training objective. So what is the simplified training objective? Because in vanilla DSP, the training target for both forward and backward models is complex. It is hard to understand the physical meaning, so we propose a simplified version of training loss. So this is a simplified version of that for backward and forward. But look at this. You are sampling from forward at each step. We call K plus 1. And for the forward, you sample from Q. So it's a reparameterized diffusion Schrodinger bridge. Because score-based generative models employ neural network like it. I have a playlist for this score matching that you can see how we learn the score by this neural network ST of X. Another proposition, terminal reparameterized DSP. So we design two neural networks to output the terminal points of the forward and backward trajectories. So these are the losses. Flow reparameterized DSP. Following flow matching, they also showed that we can see it as a flow matching problem, which is interesting. And the algorithm for training dynamic generative models. We have prior distribution, we have data distribution. Then we sample from data, we sample from prior. So this is xn, x0. Once we have x0 and xn, we get the noise sample. Okay, get prediction. Okay, we compute the loss. And we get the backpropagation. Okay, so there are specific choices of different methods and training rounds are and noise samples x sub k. So this is the simplified diffusion Schrodinger bridge in this paper that they did for backward and the forward.